Okay, before I start talking about what we're going to be discussing in this lesson here, um, let's go ahead and just review where we're at. So remember, we've computed my instantaneous power, and we've gotten it to be capital P times capital P cosine of 2 omega t minus Q times the sine of 2 omega t. Now, the reality is what's important to us is we're going to want to be able to determine what these P and this Q are. That's what we're going to want to do when we start doing circuit analysis. So that's what we want to find. But we already have some equations here. We have that P, which is my average power. I was going to write Rauer. Average power is equal to Vm Im over 2 times the cosine of theta v minus theta I. And then we also had Q, which we called reactive power. This was equal to Vm Im over 2 sine of theta v minus theta I. And just remember here, I didn't put the units here, watts for average power, and then we had this volt amp reactive var for reactive power. And the other two things we had here was that the power factor was simply PF, and that was cosine of theta v minus theta I. And then we have the reactive factor, which is sine of theta v minus theta I. Now, in another couple lessons, we will get back to circuit analysis and look at how doing circuit analysis can I compute all four of these things. But for now, we're just looking at these equations, trying to understand them, and going through some examples like we did at the last lesson where we just were given the information, we computed PQ, PF, and RF. Alright, so the next thing we need to talk about though before we actually get into circuit analysis is RMS values. Now RMS values stands for root mean square. Okay, so to actually get the RMS value of something, if you have some function, let's just say f at t RMS would simply be equal to, well, it's a square root of a mean, so that's an average, so that would be, and since we're doing with periods of periodic signals here, 1 over t minus t over 2 to t over 2 f at t dt, except I'm supposed to square that term. Now there's a reason why you just want to square it, because again, if you just look at the integral of a sinusoid, remember if you look at the integral over a period here, this is one period, you look over the integral here, you're going to have positive area, negative area that are exactly the same, and they're going to cancel each other out. So if you square it, you'll get something, that kind of looks like this, and then you'll get some non-negative areas there. And then of course if you square it, we want to have consistency with units, so we would take the square root at the end here. Alright, so let's go ahead and do a very simple example here. And now this is very important. This is only for sine and cosine functions. Other signals, for instance, square waves, triangle waves, ramp functions, and of course there's other ones as well, have different RMS equations. Or I'll say not equations, RMS values is what I'll put. And you'll understand what I mean by value in a second, because the equation for RMS is the same. You use the same equation to find RMS, but what we're going to do is we're going to get a result here which makes things a little bit nicer for us. So what do we get here? Well, let's go ahead and look at a voltage here. So I'm just going to have a voltage that is equal to Vm cosine, and for simplicity I will just say omega t. I'm not going to worry about a phase shift. And so then I'm going to integrate this, square this and integrate it. So I'm going to kind of not do all of it in one step here. So I'm going to look at the average value, and so this is going to be minus t over 2 to t over 2, and then it's going to be squared, so this would be Vm squared cosine squared omega t dt. But now I have to figure out how to integrate cosine squared, which we should know and remember how to do from calculus. But if we do that, we get 1 over t using a trig identity, Vm squared times 1 plus 1 plus cosine of 2 omega t over 2 dt. Alright, so now that we have this trig identity applied, I'm going to go ahead and pull a few things out here. So I'm going to pull the 2 out. So we have Vm squared over 2t, and then we would have integral from minus t over 2 to t over 2, 1 plus cosine 2 omega t dt. But wait a minute, same kind of thought process here. That portion's going to be 0, that portion's just going to be t, and so we get here Vm squared over 2. So then my voltage RMS value is equal to the square root of Vm squared over 2, which would just be Vm over the square root of 2. So now when I say VRMS, again, this is for sine slash cosine is equal to Vm over the square root of 2. And this is where I'm saying there's different formulas or different equations. It's not going to be Vm over the square root of 2 for all periodic signals. If you have a ramp function or a triangle wave, square wave, they might have different ones. One of them, I can't remember which one, is Vm over the square root of 3. Fortunately for us, we're going to be dealing with sinusoids in this chapter primarily, so we're going to always be able to use the Vm over the square root of 2 for RMS value. Now, some texts like to call this, instead of RMS, they call this an effective voltage. So if you see, and if your author of your textbook has V effective, that is referring to VRMS, which is equal to Vm over the square root of 2. Now, we could go through the exact same equation and get an RMS value for I, which would be Im over the square root of 2. So who cares about RMS? Why would we care about RMS? Well, there's several reasons you care about RMS. One, if you're using a multimeter and you're measuring an AC signal, the voltage, that voltage that's getting reported back usually on a multimeter is an RMS value. So, that's what you get on your multimeter. But there's something else that you can look at here. Let's look at what V effective times I effective would be. Well, that would be Vm over the square root of 2 times Im over the square root of 2, which is Vm Im over 2. But wait a minute. That's just capital P, my average power. Oh, I should be careful here. That is not capital P, but that is the well, that's the portion from the cosine function. And it is going to turn out, in a lot of cases, to be our average power. But that's front portion in front of the cosine function. All right. So that's all I really want to talk about as far as RMS values here. We're actually almost ready to start analyzing circuits. So to kind of wrap up this idea here before we start analyzing circuits, which we'll do in the next lesson here, I want to talk about something called complex power. And so we're going to define this here as S is equal to P plus JQ. So we have P and Q here, which this is going to be my average power and my reactive power. So if you want to look at what we're doing here, is we're actually kind of defining these again with phasors here. And what we said here, if we want to think about this as a diagram, we have my real axis and we have my imaginary axis. And we said that the average power, that's the real power that I can get a hold of and that I can use to turn a crank. So maybe this is, my real power. But then I might have some imaginary power to maintain magnetic fields, for instance. And so this would be my imaginary power. And then this vector right here would be S. That's my complex power. So it contains both the average power and the reactive power. And then we also have here that the magnitude of S is what we call the apparent power. And S has units of volt amps. Now, I know you might say this seems a little confusing right now. We're going to go over complex power in more detail. I just wanted to introduce it here. The next lesson we'll kind of do an example dealing with complex power and see how we can use this to figure out impedances and things of that nature. And then we'll finally start getting into some circuit analysis on here. So maybe, if you're done watching it, the video, you can pause it, but let's just maybe review again here at the end where we're at. So again, we have P, which is my average power, Vm Im over 2 times cosine of theta V minus theta I, which we now have also just learned is equal to V effective I effective cosine of theta v minus theta I, because of the RMS values that we were doing. And we have my reactive power, which is Vm Im over 2 sine of theta v minus theta I, which again, using my RMS values, is V effective I effective sine of theta v minus theta I. And in here, this cosine of theta v minus theta I is my power factor, and this sine of theta v minus theta I is my reactive factor. And then we've defined complex power as S is equal to P plus JQ, and this has got units of volt amps. Alright, so that's where we're at. And then, as I said, in the next lesson we're going to go over an example with complex power, and then we'll finally be able to start getting into how do we do circuit analysis here, and compute, not just compute these, but be able to do circuit analysis to compute average power, reactive power, complex power, just from circuit elements.